Hi, you're right. How you going? Just want to talk you through your medieval machines investigation. So this is a task that we're going to be doing alongside humanities. So you've done a bit of research in humanities on a medieval machine, and I'm just going to flick over to that task now. So what you've been doing in humanities is researching some different medieval machines. So actually, let me just zoom in a little bit here. So to design and build a simple machine used in medieval times. In humanities, you're going to be researching different medieval machines and choosing one to further explore. And then in science, we're going to undergo a bit of an intensive. So it's going to be a whole day, try and build a prototype of the machine. So just reading through your humanities work, you're researching at least 3 different types of medieval machines. So an example is a castle with a working drawbridge, a treadwheel crane, a long bow and arrow, an arbalest crossbow, windmill, water wheel, trebuchet, and catapult. So what all of these have in common is that they have moving parts, and that's going to benefit us when it comes to science, because in science what we're doing is looking at the energy transfers and transformations that are occurring. So there's some sort of mechanistic action by which these medieval machines work, so that's going to become important. So look, in humanities, you're getting a machine, finding a primary source and a secondary source, and outlining your research. So that's going to be your groundwork for this task. And then you're going to say, the machine I'm going to build is, and this is going to be the labeled diagram of the machine. So that's going to come into play when you're looking at your investigation. So now this is the STEM design cycle that you've been used to, that we've been using a lot this year. So the beginning bit is ask. So what is the problem, and define the constraints. So I'm just going to read through this with you guys. Simple machines have been around since the time of cavemen. They would have used levers to move items and wedges to cut. As civilizations evolved, so too did machines. This led to combining of multiple simple machines to perform a multi-stage process. In medieval times, society was very dependent on what were often very large simple machines, scaled up in size to create large forces. Water wheels and windmills, trebuchets, moat crossing bridges, ballistae are some examples that were based on the design of simple machines. So we've got a few pictures of things like catapults, ballistas, and the like. So in humanities, you're researching them, and there's the examples that I literally just outlined previously. And if you've got another idea and you want to negotiate it with your teachers, you can do that. So keep in mind, in science, we're going to have to identify where energy is being transferred or transformed as the simple machine operates. So if you have a stationary machine that doesn't really have any moving parts or do anything, that's going to make that part really hard. There will be a large range of materials on offer. Please negotiate this with your teacher. So I just want to outline what those materials might be. So I'm just going to flick here. What we're going to try and provide you guys with is a hairdryer, stopwatch, meter ruler, electronic balance, a glue gun, 1 stick of glue for the glue gun. We can't use too much glue. A heat mat and bench mat for underneath the glue gun. Scissors, ruler, PVA glue, tape, rubber bands, A4 sheets of cardboard, core flute, golf ball size piece of plasticine, half a strip of glue tack, 20 pop sticks, 4 bamboo skewers, 4 pipe cleaners, 3 cups, 50 centimeters of string, 8 thumbtacks, 4 split pins. You do not need to use all of that. You might need to use something different, but realistically, we just want to provide you with some resources to be able to build something substantial. If you want to use anything a bit bigger, a bit beefier, you are more than welcome, and you are encouraged to bring materials from home. We will try to source more materials, but at this stage, this is the foundation upon which you can build. So the imagine is trying to think of how is this going to start, okay? So first of all, we need a definition. What's a simple machine? What's an energy transfer? And what's an energy transformation? That will give you some grounding as to what it is that we're going to make. Then we research the different types of medieval machines. You've probably done that in humanities at this point, and you can just transfer that information over and brainstorm ways to create a working 21st century replica of this machine. Now, it has to be working because we're going to do a science experiment based on it. Now, I've said a 21st century replica is because we are making a copy or a model of a machine. It might not be exactly the same, okay? So that's why we've got the word replica in there. It can be similar, but it's not going to be the exact same thing. Accuracy is not the most important aspect of this machine. It needs to work. That's the most important thing. So the summary of research, this is linking with humanities. So you've chosen a medieval machine to further explore and construct. Now your research and what you actually make might be different depending on who you're grouped with. So depending on how your teacher assigns your groups, for my class, I'm most likely going to assign groups. You may be assigned a group with someone that's done or researched a different machine. Now you might have to vote which one you're going to do based on your research. You might have one person say, I think we should do this because of these reasons. Another person might have a different idea, and then you choose to go forward. Essentially, if your research is slightly different to what you build, that's okay. All right, but the research still needs to happen. Describe in simple steps how the machine works. Where possible, identify parts of the machine which use any of the simple machines in the table above. Diagrams will support your answer. So basically, a machine might, or the device we're making, might be made of more simple machines. So a simple lever might actually play a big role in the whole machine. So brainstorm, how are we going to make the working prototype? So what materials are going to be used? How are they going to work? Where's the moving parts, etc. Now, you're not going to just be able to conjure that up out of thin air unless you've done something like this before, or you're very, very cluey in terms of building. You're going to have to research. So if you're building a catapult, you have to research how to build a catapult, examples of building a catapult. You might Google search school catapult or something like that, where you find ideas and find designs and find examples, and you might say, yes, this looks good, but I need to change this because I don't have access to this material, etc., etc. You might find something perfect and you think, wow, that's exactly what I want to build. I'm going to copy that as best as I can. That's absolutely fine. We're not asking you to make something completely new. This type of stuff has been done before, so you need to research what's viable for you to build. This planning phase is really important. Remember, you want to keep the process described above the same or similar. So you don't want to change too much. Then we're going to plan. So sketch the machine, label each of the materials used, annotate the sketch by explaining what each part of the machine does, list the materials you will require to build, and test the effectiveness of your machine. So this is what we're aiming to do before the intensive building day, because if we don't get this done beforehand, we're going to be doing it on the fly on the day, and it's going to be a catastrophic failure. If you fail to plan, you plan to fail. That is the saying. So this part is really, really important. Then create. Create your medieval machine, record any changes you make to the design, take photos of your simple machine, include it in this section. So this is going to be the intensive building day. You take photos as you go, photo, 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 photo. It's going to be awesome. You're building the machine. To demonstrate your understanding of energy transfers and transformations, you need to complete the flow charts below. So these flow charts, and I should rotate this for us. Okay, so basically the top is going to talk or have a flow chart in terms of the energy transfers. So where's energy going? So from one part of the machine to the next part of the machine to the next part of the machine. The second is saying a flow chart by how the machine operates. So where does the energy get input in the first place? Where does it go to then? What happens then, etc. And then a flow chart of energy transformations. So kind of like our Sankey diagrams that we've been drawing. So what types of energy transfers are there happening? You can have the energy, the wasted energy coming off as well, if you're so inclined, heat, for example. Then the improve section, we're going to design a mini experiment to test the effectiveness of our machine. So basically you're going to come up with an experiment to test a certain variable from your machine. So a simple scientific practical. So it might be, if I can give you an example, if you're doing some sort of device that fires something, so a catapult, a bow and arrow, a ballista, something like that, you might want to change the angle at which the machine is firing and test how that affects the distance that the object is firing. So if you have a catapult, you might measure the angle and you might go, okay, 30 degrees versus 50 degrees versus 70 degrees versus 90 degrees. Well, you wouldn't go 90 because that's straight up and straight down, but anyway. And then you decide how that affects the distance. So this is our planning for our scientific experiment, just like we regularly do. So what is the one thing you're going to change? Okay. And for each trial, how are you going to make it different? So basically, if I'm changing the angle, I would say for the first trial, this is the angle, then this is the angle, then this is the angle, changing that. What am I measuring? So that's called the dependent variable, like we've done before. And then the controlled variables, this is what I'm going to try and keep the same every single time. You make a prediction before you start. You have your equipment, so it might be things like you might need a tape measure, a ruler, or a stopwatch. Basically, just write down what it is that you need. You need to identify safety, RIP, risk injury prevention. So what's the risk of the design? So if you're firing something, it could be the projectile, that's the risk. So the fact that you're firing something. What's the injury? Someone could be hit, even in a particular body part, the eye or something like that. And what can we do to prevent that injury? Perhaps we need to have a corner of a room where no one else is going to get into the firing zone, or you mark out the firing zone, or you make sure all the participants are wearing safety glasses. Essentially just making sure that that risk that you've identified is prevented to prevent the injury. How you're going to carry out the experiment, have your, method there needs to be detailed enough so someone else could read it and say, okay, these are the instructions for this experiment. So someone else needs to be able to carry it out. And then you're recording your results in a table. So this is the title of your table. You draw up your own results table here. So obviously columns, and they're labeled in terms of what's the independent, what's the dependent. And if you've got multiple trials, trial 1, 2, 3, and you're averaging out the results, if you're not sure about this and you're thinking, well, how do I draw up my results table? Have a look at some previous experiments that we've done this year where we've provided you the results table, and you can utilize those in order to create your results table. Here's your graph. So you're transforming your table of results into a graph of results where you've got your dependent and independent variable. So dependent on the y-axis and independent on the x-axis. So if this one is the angle of firing a projectile, and you've got that there. Remember, when you're plotting a graph, you need to have consistent increments. So if my example previously where I said 30 degrees, 50 degrees, 70 degrees, I wouldn't just go 0, because 0 has to be at the origin. You wouldn't go 0, 30, 50, 70. You wouldn't just, you have to basically plot it all out. So it'd be 0, 10, 20, 30, so 30 would be there, 40, 50, so that would be there, 60, 70, so that would be there. So you make sure that the increments are the same, so in that case it would be 10. And then the dependent variable in that case would be the distance. Try to use all of your graphs, so go all the way up if possible, or use the most of it. You don't only use a part of it, so you need to change the scale, okay? Show your teacher, if you try a graph and they'll give you some advice in terms of, I would maybe change this a little bit, or I would make these alterations. What did you find out in terms of your conclusion? Did it support or refute the hypothesis? So basically, was your prediction correct? Yes or no? Lastly is the analysis. Did the simple machine work effectively, and what were the challenges? So this is an individual reflection where you want to try and be honest. We're not expecting this to go perfect. There's going to be something that goes wrong. Maybe your planning could have been improved. Maybe the making could have been improved, the building. Maybe you needed different materials. Maybe something that you tried to put together didn't work so well. We're expecting that, and where you, analyze that and think about how it could be improved next time. That's what we're hoping that you do, that you learn from this design process. Maybe you've done this before, this design process, and you say, well, I've done this type of thing before, so therefore I felt a bit more confident when I was actually working through it. Efficiency is to do with science. In what areas did you see energy being lost? How could you improve your machine to reduce the amount of energy that's being wasted? So we're talking about efficient energy transfers in that case. If there's too much movement that's not really making the machine operate, or that it's too noisy or something like that, then you've got wasted energy. Every transformation has some energy that's being wasted. I can hear my cat meowing at me, so it's probably time to wrap it up pretty soon. Comparing the designs, interview at least 2 other groups. So take a photo of their machine. Taking a photo is much easier than sketching it. So take a photo of their machine and just explain what they've told you about their machine. So this is their machine, this is what they did, these were the energy transformations that occurred. Which design was the most reliable out of yours and the other 2 that you looked at, and how did you know? So reliable means it works well when you want it to work. If I build a catapult and it only fires every 5 times I actually try to make it fire, that's not very reliable. If you've got a machine like a bow and arrow and it works well every single time, then that's very reliable. Which design was the most energy efficient? How well do you know? Usually you're going to know based on the energy output. So whatever the machine's trying to do, if it does it well, then that's going to be the most energy efficient. The last here is your self-assessment on our collaboration. So this is just putting dots or ticks in there in terms of how you felt you collaborated with your 3-person group. So guys, this is a long task, but we are working on it on a day intensive. So there's going to be lots of time in order to really build and test this thing as much as possible. I'm really looking forward to seeing what you guys can come up with. And feel free to obviously look back at this video if you need any support. Thanks very much. Bye.